Welcome to UVU CS3060 Lecture 5.5, where we discuss the multi-level queue scheduler. So, very frequently, we have our ready queue divided up into separate different queues. We'll have a queue of jobs that need to be interactive, meaning that we want those particular jobs to have a fairly quick response time, not suffering from anything like the convoy effect. But then there's usually a lower level or lower priority queue for background processes where we don't need interactivity. Those jobs can run when there's spare cycles to be run, but the jobs do need to be taken care of. This allows interactive jobs to be processed much more quickly, while these background jobs, which don't need interactivity, can wait around until there's time given to them. Now, frequently in this particular setup where you have multiple levels of queues, a process will be assigned to a specific queue in this setup. So when a job is assigned to the background queue, it will always be a background job and will always get pushed back to the bottom of the background queue. Typically, most of these queues will have different scheduling algorithms. Round robin for interactive foreground processes, and then something like first come, first serve as in the background. Sometimes you'll have more than 2 levels to the queue, and you may also have priority-based queues, such as shortest job first or shortest runtime first. Now, in the case of when it comes to these particular multi-level queues, something that's very important to remember is that jobs in an upper level of the queue must all be complete before the background will start processing. So foreground would have to be job number equals 0, so no jobs in the queue, before any of the background jobs can be processed. Now remember, these background jobs are just batch jobs. They can run anytime. But in this particular type of system, if we constantly have jobs in the foreground queue, then that causes starvation in any of the lower queues, such as the background queue. We call this fixed priority scheduling, that we have everything done first in an upper queue before it goes to a lower queue. Now, there is a way in multi-level queues to actually give each queue a certain amount of time, kind of like a round robin scheduler for the multi-level queue. In this case, we assign a time slice. So perhaps the foreground processes get 80% of the CPU time, and then 20% for the background. This gets rid of reduces the starvation that is experienced. But there's a balancing act here. Do you choose 80 to 20 or do you choose 90 to 10? How do you prioritize these things? And that's a hard choice to make. And so we can see here's a 5-level queue. We have system processes at the very highest priority. This might be a shortest job first, but very rarely do system processes get put here, only when they're absolutely needed. Interactive processes, these are where most of the user space processes end up. So the processes where you as a user are running a program and need some form of interactivity. Round robin is usually a pretty good one. So let's go ahead and we'll put shortest job first here. This will be a shortest job first queue. This will be a round robin queue. The next level, you might have interactive editing processes where you don't need the same kind of responsiveness. Maybe these have I/O wait times that are enormous because you, as a stupid lumbering user, take a long time to press a key. This may also be a round robin type of affair. So we can have the same type of scheduling, but these interactive jobs get to happen before interactive editing jobs. Batch processes. Batch processes could be a first in, first out. Type of affair. And student processes, because students are always the lowest priority, could also be first in, first out. In any case, a multi-level queue allows you to specify a process and what type of scheduling it should experience in relation to all of the other processes running on the system. Again, all higher priority queues must be empty before the lower priorities can be executed. So a student process that is scheduled on this particular queue would only run after everything else above it and all the other queues was completed. Now, as you can imagine, if you were a student on a very busy system, your job would never get run. So, in some cases, a multi-level queue will actually allow jobs to move between the various queues depending on the age of a particular job. Let's say your student job is taking particularly long to execute. Well, the operating system would keep track of that. It would keep track that your job has just not received CPU time like it deserves. And so what will happen is, in a multi-level feedback queue, the scheduler will actually move jobs between the different queues. It will generally move a job up the queue, giving it a higher priority until it actually runs, at which time it will move back down the queue. Multi-level feedback queue schedulers have several. We have the number of queues, which any multi-level queue will have. The scheduling algorithm for each queue, we've already discussed that. The method used to determine when to upgrade a process and to downgrade or demote a process. This is what makes the feedback queue, multi-level feedback queue, unique. There's an algorithm that actually determines when to upgrade a process and what method will be used to determine which queue a process will enter when the process needs servicing. When I run a job, how does it know which queue to put that particular job in? Well, there must be an algorithm to help deal with that. So, here's a multi-level feedback queue example. We have 3 queues. We have a round-robin queue, with a time quantum of 8. We have another level with a round-robin scheduling, a time quantum of 6, and then we have the first-come, first-serve queue at the very bottom here. So, we have a job in this particular example, a job that enters queue 0, the top queue, which really which should be served by first come first served. But when it gets the CPU, the job receives 8 milliseconds. If it does not finish its 8 milliseconds, it actually gets downgraded to the second level queue. So what that does is jobs that are less than 8 milliseconds will actually, as they come into the queue, will get run fairly quickly. If a job's going to take longer than 8 milliseconds, it will get moved down to a lower queue so that it can still get time. It will still be queued, but it will have to wait for the Q0 to be processed. Now, once the upper level queue, Q0, processes all of its jobs, it can go back to the job that that ran on there but went beyond its time quantum. Now that's a round robin, and it gets processed for 60 milliseconds. If it still doesn't complete, it actually drops down one more level to the first come first serve queue, which of course will allow that job to run to completion, but it will have to wait for all other jobs to complete. So let's say the job is actually a 30 milliseconds. So job 1 is 30 milliseconds when it comes in here. When it leaves here, that job 1 gets moved to this lower queue where it has 22 milliseconds still left to run in its CPU burst. All the jobs up here in the Q0 will continue to run, but eventually that queue will empty, and this job can actually run for 16 milliseconds. Since it's not going to complete before the 16 milliseconds, it will be moved down here so that job 1 will have 6 milliseconds still, but it will wait for all of these to complete. Once all of these queues are empty, then the first come first serve may operate on this, at which point it will run to completion, because remember, first come first serve is non-preemptive, and it will end up with 0 milliseconds when it's done with that queue. This ends UVU CS3060 Lecture 5.5, where we discuss the multi-level queue scheduler.